Check it out now, y'all.
NanoHub U, online instruction.
Okay, welcome back. This is the last lecture of the second week, and we'd like to discuss the one-dimensional quantum harmonic oscillator potential and the solutions of Schrödinger equation when this potential energy term U of x varies quadratically with position x. So that's the content of this lecture. We're going to make use of a lot of the concepts that were discussed in the prior two lectures. So even though the arithmetic here is a lot more complicated than in the prior lectures, if you've been following those lectures, you'll understand the concepts, and hopefully the discussion can be facilitated accordingly. So I'd like to start off by discussing the harmonic oscillator potential well and try to make sure that it's clear to everybody what problem we're exactly worried about in this lecture. If you confine a mass m to a harmonic oscillator potential classically, it just simply means that this potential energy function U of x, it's often written as V of x, different textbooks, is equal to 1/2 times a constant times x squared, right? And this constant can be written in a number of different ways. One way is it involves the mass of the particle oscillating in this well times the frequency, the angular frequency squared, right? You can define a spring constant k in terms of this m omega naught squared, and then you can rewrite this as 1/2 kx squared, which is possibly a little bit more familiar way of writing the potential energy, right? The point is that this constant in front of the x squared, that constant controls how quickly the potential well rises. So let's talk about the classical case to begin with. What I've got is a sketch of a quadratic potential well. The premise here is that you've got a mass m that oscillates in that potential well. That mass m is usually released at some point, and that release point is referred to as the total energy that the particle has in this well. As the particle oscillates back and forth in the well, right, its kinetic energy increases and decreases periodically, right? At the release point, clearly the kinetic energy is equal to 0. When the particle rolls down and gets to the bottom of the well, then the kinetic energy has got a maximum value. And at any point in between, right, the potential energy and the kinetic energy are going to oscillate back and forth between 0 and a maximum value given by this parameter E total. The release point of this particle, as it oscillates back and forth in this well, the release point is referred to as the turning point. And classically, the particle is confined to this region of space between, let's say, x0 and minus x0, right? And the particle can never get higher in energy than is specified by its release point, by these turning points. So this is, of course, the case when there's no friction involved, right? If there's friction involved, then clearly the particle amplitude of the particle oscillation will decrease with time. But if there's no friction, right, the particle will just oscillate back and forth forever, always achieving this same turning point as the particle oscillates. So this is, of course, the analogy, the physical analogy here is a mass on a spring, right? If you take a mass, suspend it from a spring and release it, the mass will oscillate back and forth, and the potential energy and kinetic energy are transformed back and forth as sketched in this slide. Now, what we want to do is we want to ask what happens if that particle is treated as a quantum mechanical particle, if it has the Broglie wavelength associated with it. We want to ask in the quantum case, are there any restrictions on energy of the particle? Classically, of course, there's no restrictions on energy, right? The mass can be placed at any point along this curve, and where it's placed just before it's released, right, that specifies the energy E of the particle. No restrictions whatsoever. However, we've already seen in our discussion of a few of these simple quantum mechanical models, the energy states, you can reasonably expect them to be quantized because of the solutions of Schrödinger Equation for this particular case. So, we're going to use this value of U of X in Schrödinger's equation, and we're going to look for solutions and find out what the restrictions are on the energies. That's the program for this lecture. So, how to begin? Well, we have to begin at the beginning by writing down Schrödinger's equation. So this is, again, the general form of Schrödinger's equation. What you should have learned in this week of lectures is that U of X always depends on the problem that you're trying to solve. And in this particular case, the U of X that we're going to use is this harmonic potential that's often written in this form here. So it's quadratic in X. It's got a constant in front. It depends on the mass of the particle and the steepness of the well. There will be, again, two regions that we have to consider explicitly. There's going to be a classically allowed region, and that classically allowed region is going to be defined by the two turning points, the two classical turning points of this particle of mass m as it oscillates in this potential well. And then there's going to be a classically forbidden region, right, where it's possible quantum mechanically for the particle to actually go to regions in position x, which are greater than the turning points, the classical turning points that you would expect based on this interaction potential energy. So the two differential equations that have to be solved, okay, can be written down, and what we need to do is we need to look for solutions to those differential equations. Well, the solutions are complicated. I'll tell you that up front right now. A guy by the name of Hermite discovered the analytical solutions for differential equations of this form, and now there are tables listing these differential equations. We're not going to derive the solution of these differential equations. We're just going to take those known solutions and try to convince you that they do solve the differential equation, and then see what the consequence of those wave functions are. So to make a long story very short, the known solutions of a differential equation that has this form, the known solutions involve an exponential, which is quadratic in x. There's a constant b, and this constant b is related to constants that appear in Schrödinger's equation. And then multiplying this exponential function, there's something called a Hermite polynomial, which we'll talk about in the next slide. And these Hermite polynomials are subscripted by an index n, which basically tell you the quantum state of the particle that is accessed, that is obtained when a particle has a wave function specified by an equation of this form. So these Hermite polynomials are complicated objects that basically oscillate with position. And what I do here is I just plot a few of the first few Hermite polynomials, right? If you see the Hermite polynomial when n is equal to 0, that's just a constant value that's given by this red line here. When the quantum index n is equal to 1, then the Hermite polynomial is a straight line indicated by this gold line here. When n is equal to 2, the Hermite polynomial is quadratic in x. That's indicated by this green line. as you go to higher order indices n, right, these Hermite polynomials acquire wiggles, oscillations, and you can find tables that list these Hermite polynomials. What I do is I write down explicitly the first few solutions to Schrödinger's equations using the first 2 or 3 Hermite polynomials. So, for instance, the lowest wave function, the lowest energy wave function, is given by the constant Hermite polynomial for n is equal to 0. It's some constant a0. It's exponential with the x squared dependence constants that come out of Schrödinger's equation. The next solution allowed is when the quantum index n is equal to 1. Now the Hermite polynomial is linear in x. We still have this exponential function multiplying it. And then likewise, as you go to higher quantum indexes, n equals 2 and 3, and so forth, you pick up other factors that multiply this quadratic exponential function here. So those are the known solutions. I think it's worthwhile to verify that these proposed solutions do in fact satisfy Schrödinger's equation, and so that's what I work through in this slide. I actually take the n equals 1 solution and I plug it into Schrödinger's equation. Right. The point is that now the energy for this n equals 1 solution is going to be subscripted by the index 1 to correspond to the n equals 1 quantum state. And the issue is, with those known solutions of Schrödinger's equation, what is the allowed energy E1 for this first quantum state? So I write down the wave function that we're going to use. I do some simple algebra to make I transform some variables, and then I just simply put this equation into this differential equation, take the second derivative, and work through the consequences. And what you find at the end of that exercise is that this parameter E1 that appeared up here has to equal 3/2 h bar omega naught, where omega naught is the resonant frequency that this particle exhibits as it oscillates back and forth in this quantum well. And so for the n equals 1 quantum state, the allowed energy turns out to be 3/2 h bar omega naught. The next slide, I actually list the energy eigenvalues for different quantum numbers n, and the quadratic potential well is notable because of the extremely simple form for the energy eigenvalues. Right, so you can see that the energy eigenvalues follow an equation that's given by n plus 1/2 times h bar omega naught, where n is the quantum index of the state that the particle is in. So you've got this ladder, this discrete ladder of allowed energy states that are given by solutions to Schrödinger's equation, and then I also list the normalized wave functions or eigenfunctions for each quantum index n. So these normalized eigenfunctions were obtained by insisting that the wave function times its complex conjugate, when integrated over all space x, that's equal to 1, and that determines all these these multiplicative constants, which are in red in this table. So the notable thing about the harmonic oscillator potential is this quantized ladder of energy states, separated one from another by an integer. It's kind of useful to visualize some of these wave functions, and that's what we do in this slide. So this sort of summarizes the discussion, right? What I do here is I plot the wave functions for the first 4 quantum states, n equals 0, n equals 1, 2, and 3. Right? You see that in all cases, the turning points are indicated by these dashed lines. Right? These are the classical turning points. In all cases, the wave function decays exponentially outside that turning point. Right? So you can see in all of these eigenfunctions, they have this exponentially damped region. In the middle, in the region, in the classically allowed region of space, the wave function just undergoes an oscillation that's given by these Hermite polynomials. The allowed energy levels are specified. They're equally spaced, right? And so you can start to plot the position of these allowed energy levels within the context of this parabolic potential well. The separation between each energy level is just given by this constant h bar times omega naught, as we defined in the second slide of the lecture. Again, the wave functions don't tell you anything physical. That's one of the main messages you should take away from this discussion. It's the square of the wave functions that give you the information about where the particle is located. And so for that reason, on this slide, what I do is I plot the wave functions and then the square of the wave functions right next to one another so you can see the consequences. And so right away we can go to the probability distributions of the particle in this potential well. You can see that for some of these higher order quantum states, there are regions where, or specific values of x, where the probability goes to 0. That's because the wave function, in fact, has a 0 crossing at those points. So if you did an experiment, put a particle in a harmonic quantum well, right, and you put it, let's say, in the n equals 3 state, there would be 0 probability that you would find that quantum particle at certain locations. Conversely, there would be maximum values of the probability where the particle would be most likely to be found. And so you can interpret, once you know the wave functions, you can interpret where the particle is likely to be located by simply just taking the psi times psi square and making plots of that. I show a more complicated example. Here I take the 10th quantum state and I plot it's the square of its wave function. And what you can see is that now there are many values of x where the quantum probability actually goes to 0. So there's actually 10 nodes where there's 0 probability of finding the wave function, or finding the particle if you did an experiment. So this sort of ends our discussion of these classic models. I'd like to try one last time to summarize the results of the previous 3 lectures in one slide. And here what I do is show you the analytical solutions for the energy eigenvalues of a quantum particle in an infinite square well, in a finite square well, and in this harmonic oscillator potential well. Right? The results for the infinite square well over here are analytical. The results for the harmonic oscillator potential well shown over here, those are analytical. If you want to find out the energy eigenvalues for a finite square well, you're going to have to do some work. You're going to have to do some numerical calculation. So it's for this reason that you very often see predictions based on either the infinite square well or the harmonic oscillator potential, because those solutions are well known, they're analytical, they can be written down in very compact form. So it's really important for you to understand these 3 problems and understand the various steps that you have to go through in order to get these energy eigenvalues. This is a process that we're going to follow over and over again throughout the semester as we investigate more and more complicated problems using Schrödinger's equation. And Of course, what I still have to convince you of is that these predictions do in fact match experimental results. And so we'll start working on that in the next few weeks of lectures, where we'll actually do calculations based on Schrödinger's equation and compare those calculations to experiment. Of course, the agreement is extremely good if the model for U of X matches what you can achieve in the lab. And it's one of the great triumphs of physics from the 1920s up until the present. The predictions of Schrödinger's equations have been verified over and over many times. We'll try to emphasize that and reinforce that as the semester evolves. So thank you for your attention, and you'll have to work through these notes if you want to understand them. You just can't read them, so please spend a few minutes checking the algebra and making sure you understand how you can get from one line to the next. All the steps are provided. It's up to you to put the effort in to try and understand them. Okay, see you next week.